So, hello everyone. This is Leonardo De Laurentiis. Let me just put my mask off. Hi everyone. I'm a research fellow at ESA Esbrin, and I welcome you to this side event, which is called AI for Data Quality. And we're in the framework of the 4th edition of the ESA Phiweek. This side event aims to bring together the artificial intelligence and the Earth observation communities towards a joint effort to provide innovative AI-powered tools and techniques enhancing Earth observation data quality, both for the SAR and the optical domains. So basically, during these years, the rise of new space economy and the exponential increase of available Earth observation data, new concepts and old concepts such as data interoperability, harmonization, comparability, and quality control are more relevant than ever. And the huge amount of Earth observation data also calls for new and innovative big data-oriented approaches, among which AI-powered techniques may represent an effective framework to achieve unprecedented results. So with this spirit and with this view, today we invited our 4 speakers that will present the latest achievements in the area and will provide their view and some cues. This will open the subsequent open discussion at which everyone is called to take part. Also from the audience, the attendees, please, you're very welcome to join and jump in. As we would like to collect ideas and suggestions on what HESA should might to provide to help the AI and Earth observation communities working better together towards AI-powered data quality. So 4 speakers, I would like to remind you that you have 15 minutes slot for your presentations and questions and answers. So maybe 10-5 is a good division. Our 4 speakers will present the latest achievements and provide their view and opinion on the AI for data quality, future developments, and maybe also provide comments on what HESA, how outside we should do, might do, or provide to help those communities work together. The participants and the attendees can interact mainly through the chat, and if any of the participants would like to talk, please write. I don't know if you can raise your hand, but maybe you can write in the chat. Maybe I can allow you to speak, or if you have something that you wish to write, you can just go and write down, and I would like to, and I'd be happy to share with the speakers and with the attendees, with the other attendees. So I would like to remember another important thing, which is that the event will be recorded and which will be used for the ESA Phiweek related purposes. So mainly the Brella platform. So any participant which is feeling uncomfortable with that may keep the video disabled during the event and also the audio. So I'm glad to introduce our first speaker, which is Professor Jan-Peter Müller. Good afternoon, Prof. Müller. Thanks for joining again. Prof. Müller is head of the imaging group at UCL MSSL, where he currently works on the application of deep learning to super resolution 3D surface modeling and 3D cloud motion capture. For 40 years, he's working on NASA and HESA scientists to develop new essential climate products focusing on the Earth as well as on Mars, the Moon, and Jupiter. Prof. Müller will present strategies for assessing the uncertainties associated with deep learning applications in remote sensing. So, Prof. Müller, the floor is yours.
Thank you very much, Leo.
I guess you can share, can you? Right, you can share. At least I can see the slides, I guess.
Yeah, hopefully everyone else can.
Is able to do that.
So
right, the floor is yours.
Yeah, so I'm going to talk about some recent work. I'm not going to cover the automatic retrieval of 3D surface information, because so far we haven't applied that to Earth observation, only to terrain modeling of the surface of Mars. So I'd like to start off by giving a general overview, a definition of uncertainties versus error, because these are frequently confused. Then show how we went about estimating uncertainty for super resolution restoration, for sea ice roughness retrieval, which has only been presented so far at scientific meetings and not the underlying machine learning parts. And finally, for cloud masking as part of an ESEF sponsored Sentinel-2 high resolution albedo project. So uncertainty refers to describing the spread of a probability distribution, and this is taken from a presentation made a number of years ago as part of the EU Quality Assessment for Essential Climate Variables programme. And uncertainty is therefore the doubt you have on the particular value, and it's something that you need to calculate from the values themselves, whereas error is the difference from truth, which results from imperfections in the measurement technique or in the measurement retrieval method. And the error can be both from random and systematic effects. So in order to correct this, where an error is known, it can be corrected by applying this correction, which is derived empirically, and there'll always be an unknown residual error, which adds to the uncertainty. So it's very important we have consistency in terminology. This shows an example of where you can have accurate and imprecise versus accurate and precise versus inaccurate and imprecise and inaccurate precise. So essentially, this refers to having more random and more systematic going from left to right. So starting off first with an example of super resolution restoration, this is the process of enhancing the spatial resolution of images, or if you're dealing with video, from video frames. This kind of photo enhancement is based on the idea that the human vision system doesn't really care if the generated high frequency textures are not strictly correlated with the ground truth, as long as it looks realistic. That's at least been the main application in computer vision. Such generated high frequency textures can significantly improve the perceptual sharpness, but are considered artifacts in remote sensing and certainly artifacts in scientific applications. So in order to achieve the desired outputs for remote sensing, we need higher signal to noise ratio, we need to minimize artifacts or fake news, and we need to improve the edges and object outlines in order to achieve a higher image effective resolution. But we need to balance this against the recreation of visually realistic high frequency textures and also being able to detect small objects. Now, within the literature, a number of metrics have been proposed to be used in order to quantify this, and we've looked at several of these. So to show you an example, this is over the Bao2 test site, which is in China, in northern China, in Inner Mongolia. And we can use the structural similarity index whenever there's a reference ground truth, which in this particular case is actually laid on the ground. And here you can see an example of 31 centimeter world view images and the retrieved 9 centimeter version using an algorithm called Optigan, which is published in the paper, which is referred to on the lower left. So for this, a slanted edge measurement system was employed called EMA-test, which is a commercial-based system, in order to look at edge profile measurements, and it refers to the number of pixels for a 20 to 80% edge profile rise. So ELF, which is our own in-house system, which was developed subsequently, uses an automated image edge detection and filtering, where it measures the edge spread function, the line spread function, or the full width at half maximum. So we can also compare this, of course, for lots of different spectral bands. So here's shown as the ELF calculation system, which takes our low resolution image and our super res image, applying adaptive threshold and canny edge with Hoff line detection to find the linear elements, and then to crop the slanted edges from the regions of interest, normalize these, then calculate the edge spread function and after filtering, calculate the line spread function in order to calculate a mean full width at half maximum. This is all described in excruciating detail in our recent publication from May. So this shows a summary of the use of this edge spread function to calculate an effective resolution, which you can see varies a great deal, both from the original WorldView 3 all the way through to the Optigan performance. And one can also use the bar targets in the Bow2 CSWGCV test site in order to try and find what is the smallest resolvable object. A second application is to actually retrieve surface roughness of sea ice from the multi-angle imaging spectroradiometer which flies on the NASA EOS Terra platform, which is about to start seriously deorbiting in the middle of next year. So in this particular case, a SVR was employed using LiDAR measurements, and essentially, although the LiDAR measurements were calculated at a 1 meter, these were pulled together into the 1.1 kilometer that the multi-angle MISA imagery is calculated from, and using different angles, which in this particular case refers to 45 plus or minus 45 degrees, the BF, the BA and the nadir camera, and choosing matchups between the Operation Icebridge LiDAR and the calculated 1.1 kilometers, it's possible via the SVR to actually measure and compute a surface roughness product at a 1.1 kilometer. And this is described in a forthcoming paper from Thomas Johnson et al. And then the final part of this is taking each individual MISA swath, and here you can see the information that's used for the SVR training, producing something which covers the entire Arctic region. So we decided to employ, after trying logo techniques and various other methods, a blocked K-fold cross-validation technique. And in this case, nearby training instances are likely to be more similar than those that are further away. And if we don't account for this dependency structure in cross-validation, then we will underestimate the predictive error. Instead, we can determine the permutation of split using the blocking, but we need to ensure the class sizes are approximately equal to avoid introducing bias, which is the problem we had with logo previously. The model performance is then assessed using a blocked K-fold cross-validation scheme to reduce bias from the spatial autocorrelation. So data is split into spatial blocks, and these individual lines here refer to individual Icebridge airborne campaigns, which were conducted by the US. Spatial blocks are aggregated into folds such that each fold contains similar numbers of training incidents. And training in this case, as I said, comes from the Icebridge aircraft transects. So here we can see the model performance assessed iteratively over each fold, similar to K-fold cross-validation, and averaged to obtain an estimate of model performance. And here you can see, using the coefficient of determination, how this is done using multiple folds. The final example I want to show relates to high-resolution spectral albedo at 10 meters and 20 meters in a recent ESA project. And I'm just going to focus on one part of this and not describe the rest that was done recently at the VH-RODA and also at the RadCalNet meeting. And that is the part that's actually concerned with making the data set in order for you to be able to run, and we tested a number of them, and you'll see the results in a moment, of different deep learning techniques in order to produce a cloud mask. This is the overall schema, and what I'm going to concentrate on is the iris annotation tool, and the data set itself. If you screen capture the QR code or copy the URL, will allow you to get more details. This is all within a paper which is in the second review, and we hope will be published soon. So Alistair Francis, who's now an ESA fellow, collaborated with John Mertzaglod while Alistair was an intern from UCL and John was a young graduate trainee. And this whole idea of producing a large collection of training sets was based upon using labeled Sentinel-2 data with the emphasis placed on having a large variety of scenes as possible from all over the planet. And some 513 of these sub-scenes were taken from completely random selections of the 2018 Sentinel-2 catalogue using the open source tool and in order to produce the actual final results. Shadows were included, and we had somewhat of a 95% agreement between the two annotators on a 50 scene validation set. So there are thousands of these unique views on Zenodo, and we know that there's been many, many downloads. The model itself appears to achieve an F1 score of around 93%, and it does this equally on Sentinel-2 and Landsat 8 described in the paper. So here, for example, is the tool itself, showing you different band combinations, and then using a random forest to actually automatically or semi-automatically produce cloud masks. That is then employed iteratively, and you improve the training by just sweeping your large cursor or your adjustable sized cursor over different parts of the cloud data set. So the final results was a validation against 250 test samples with different cloud masks, and using both overall balanced accuracy as well as the F1 score and the recall and precision. You can see how this varies for the Deep Lab version 3 for Sentinel-2 and Landsat 8. The S2 cloudless scheme produces slightly better precision values, but you can see how that compares on the order of 10% better in comparison to the standard level 1C product cloud mask. What you don't get is any actual quantitative information or any feel for what is the operation of this technique. So here, for example, we can see the technique, the gray areas here are the ones that have been, the cloud mask has been detected, and the cloud mask has also been detected, but you can see that the cloud mask retrieval isn't very good when, and gap filling from times before and times after don't entirely eliminate it. Or in this particular case, where the cloud mask is not really applicable because of the fact that we're looking at thin cloud or dense aerosols in the top part of the Lombardy plain. So basically, in this particular case, we're not getting a feel for this kind of issue. So in conclusion, the next steps: users need uncertainty information for data assimilation. We need to develop as a community methods for looking at self-consistency, including the detection of bad training data and the application of self-learning systems. We desperately need something that doesn't rely on either citizen scientists or people employed in villages in North India to actually do that training. The manual methods of training and validation are extremely time-consuming and need to be replaced for every new data set. And finally, the validation against independent data sets is at the moment far too resource consuming for operational machine learning applications. So we need to address that problem. Thank you.
That's right, all good points. And thank you, Prof. Mueller, for your very interesting presentation. Is there any question from the audience? I don't see any question from the chat. I think I have a couple questions. Maybe if any of the attendees want to ask something, please jump in the chat. So you showed, Prof. Mueller, the first, let's say, application, as you call it, basically it was more a framework, right? The SSM framework. Is there any AI model or technique inside that, or it's just a deterministic approach or defined algorithms in there?
We've looked. There are some that claim this, but at this point in time, we haven't found any, but I'm interested to hear, obviously, from the other speakers about work that they may have done that address this more directly. I think the difficulty is that although we are at a stage where we can use numerical models, for example, like large eddy simulations to simulate a set of clouds, and we can use 3D radiative transfer models like in the XSIM, the Earth Care Simulator, to produce a Landsat-like image or a Centaur-2 image, and there's a similar system developed at DLR by Bernhard Meyer. The fact of the matter is that we don't capture all of the individual elements, and simulated data sets like that don't yet, at this point in time, allow us to tease out what is the uncertainty, where are the different components of the uncertainty coming from, and then how to explicitly introduce uncertainty into the machine learning process. At this point in time, I don't think we have a solution to that problem.
Right. So I see. Okay, I think there is a question from Chris. Great presentation. Is your cloud detection module configurable so that we can tune it to be very aggressive? Example, Gracia agriculture likes to flag thin haze or as clouds weather.
Yeah, very much so. I mean, the Deep Lab version 3, which is a well-known technique in machine learning, will allow you to tweak. So if you want to be more conservative, it is possible to be more aggressive, as you call it, in actually removing those cloudy features. We're interested in retrieving the albedo and i.e. the spectral reflectance, and we're prepared to go with aerosol optical depths of up to 1, but that may not be appropriate because one of the things is that we can potentially at that level, if we're employing a scheme like the SEAC scheme that we do, to provide an uncertainty which is propagated from the level 1 reflectance all the way through to the final top of canopy reflectance. In that case, of course, it may still contain valuable information in that pixel. You may not necessarily need to flag that pixel as too cloudy to use. But I think that's something that still needs a lot more empirical testing. We processed about 1,000 scenes, which are on our website, of the spectral albedo, which includes obviously the cloud masking, but we haven't produced that as a separate layer. But there's animations on there as well. So just as a piece of naked promotion there, there's hr-albedo.org. So please be our guest to take a look, and you can download any of the products.
Right. So maybe I'll leave other questions for later if you can join the final discussion. Thank you, Prof. Mueller, again. And now I'm glad to introduce our second speaker, which is Margarita Domnich. Hi, Margarita. Margarita is a PhD student at the University of Tartu and a machine learning engineer leading the HISA project, AI-based cloud mask processor for Sentinel-2. She studied computer science at National Technical University of Ukraine, University of Tartu in Estonia, and Aalto University in Finland. Besides computer vision interest, and she's a researcher in Trust AI project funded by the European Union with the aim to improve explainability of artificial intelligence. Margarita today will present Kappa Mask, AI-based cloud and cloud shadow mask processor for Sentinel-2. Margarita, if you can present, the floor is yours. I think you can. Okay.
I hope you can see my slide.
Yes, and we can hear. The floor is yours. Thank you.
Thank you so much for introduction. So yeah, I will be going to present you our AI-based cloud mask processor, which we developed in Copazeta with ISA funding. So the motivation why we start developing the CloudMask project, Capazeta is doing a lot of Earth observational application using satellite data, and one of the pain during the processing of time series for this application is incorrectly predicted cloud and cloud shadow pixels, which at 10-meter resolution interfere the results very much. They are propagating into higher level products, interfere in DVI, and existing free and open cloud masks are not accurate enough, unfortunately. So that's why our goal was to develop the most accurate cloud mask method. This we decided to narrow the focus area in the beginning to Northern European area. So if we prove to be successful in this area, we can extend the project further. And as we started from agriculture, we focused on summer season. By summer, I mean from April to October. This is usual agriculture observation period. So as a result of the project, we created an open source label dataset, which has cloud and transparent cloud shadow and clear mask. It is now published just a few months ago and is available by this link for download. And we also published a scientific article, which was published just a few days ago. So it's also available by this reference. So I will introduce the pipeline, how we develop our cloud mask. At first, we were looking for existing open source dataset. We found the dataset of Professor Miller, and we actually used it. So thanks for his work and for his dataset. So we gather open source label data and pre-train the model on it. But our cloud mask should be 10-meter resolution for agriculture. So we further developed our dataset and we fine-tune our model on it. We use the active learning methodology in the loop for developing it to increase the speed of the learning and selecting the worst performing products for labeling. And then we compare the performance on separated isolated test dataset. So as a first step, we had an open source label dataset by Francis Alistair and Professor Miller. It has 513 subscenes at 10-meter resolution. We oversampled it and pre-trained our model with this dataset. It has 3 clusters, clear cloud and cloud shadow. But in our cloud mask, we also separate further cloud for semi-transparent and cloud. So the thin cloud, it is a separate class for our dataset. So then for our dataset, we labeled it using this scheme of 6 classes. First is missing, some missed data caused by the angles of satellites. Sometimes it is missing data. And the 5th class, undefined, it is just for labeler when he or she is not sure which class these pixels belong to. But the final model is not able to predict this class. The model prediction is only like for these 5 classes, but in our data set, labeler also can put undefined classes. So to train the model on our Northern European scope, we tried carefully select all products to represent both spatial and temporal dimensions quite well. So you can see on this maps the products that we've selected for labeling. We also make sure that we are seeing different types of clouds in this product. And also from each month, from April to October, we had at least 10 products for every month. So this is our data distribution. And since one Sentinel-2 product at 10-meter resolution is a very big image, nearly 10,000 by 10,000 pixels, it is not actually possible to label the whole image, and also for as a networks, it's quite computationally expensive to train the network with such big images. So we further divided into 512 by 512 pixels. It is actually quite common practice in cloud mask methods. So all the time we are dividing big image into these batches, and then we when we run our predictor, we glue up the final picture all together. And as for active learning method, we are selecting 10 of the most worst performing and complicated subtiles from this product. And we believe that this approach will help to detect all possible problematic areas for our model. We also have some interactive tool where we can look for different subtiles and see if there is any problem on edges and which pixels have which error. Yeah, there's some fancy things. So as for the model, we then pre-trained it on open source 20-meter resolution data and we fine-tuned on our data. For training, we were using UNet method. It is modified for LNC and for L2A input. So we actually have two models, one for L2A and another for LNC, which will be comparing later. And UNet is a standard well-known network used in image segmentation, which shows very good performance, and it's also famous that it's quite lightweight. So we were also showing later the time performance, and it's actually comparable with other rule-based methods. For the evaluation, we are using isolated test set. Also, like these blue dots showing the products that are used for testing only. They were never seen by model. So we believe that on this isolated data set, it is fair to compare all models. And again, they have different types of clouds. They are presented in each month from April to October. So this is our test set. As for the results, here it shows the L2A prediction for our kappa mask. This is label on the right, and below there is rule-based Centaur and F-mask, which are for simple theme methods, and Maya, which use multi-theme input to generate the mask. As you can probably see, kappa mask here performing very well. This is test set, so it's not training. And for example, some smaller cloud shadow is captured really well, while F-mask is losing them very frequently. And smaller clouds also, Centaur is losing a lot of smaller clouds, while neural network-based model is doing much better. And this is kappa mask LNC output on one subtile. So it has semi-transparent clouds here, and again, like smaller clouds captured better, and some of the cloud shadow missed by F-mask, and Maya shapes are really like not that good as in neural networks output. We also make some web pages where you can see much more images, and you can drag this slider to see the overlaying image of the prediction. So here again, like it's visually visible that Centaur is missing smaller clouds, while neural network model is doing better. as for the metrics, we compared dice coefficient score over all algorithms in test dataset. We also used one machine learning model as to cloudless. For comparison, it has only two classes output, clear and cloud. But for those two classes, we see that percentages of neural network model is better, and especially cloud shadow improvement is 20% better than the closest competitor than Core. Yeah, so overall, all classes average is also nearly 20%. For as to cloudless, it is a bit smaller difference, but again, here is only two classes. So, at some point, we start thinking that this is the comparison for our own data set, but we need to compare on some other data set with some different labels. So we used two validation data sets from TNIX. One is bio data set and another is GSFC data set. They have a bit different interpretation of classes, and this is quite an open question to the community that we need to somehow define different how we interpret classes in all data sets so we can compare them and compare different cloud masks. So in this test bio, there's low clouds and high clouds, and they are not really directly correspond to our like sim clouds and clouds. So we combine these classes. One is cloud, and in our Kubernetes code would be also like to took it as one cloud class. So in that sense, I think it's fair. Other data set had shape files, and there is a gaps in them. So we discarded gaps and we compare only like those pixels that we know for sure that this is this class. And for the first data set, the comparison with our method and CentOS show overall that it is nearly 10% better. And for another one, the GSFC, our Kubernetes is nearly 5% better overall. And also recently we compared one of another deep learning method from University of Valencia. And we are looking for further for other cloud mask methods and to compare like our model with other ones and make some big validation on some data sets that be really creative. We can have this comparison between models. So this is some examples of big image output for L2A and for LNC model. They're looking quite well. And the final question is really neural network model is slower than other models? Why shouldn't we use neural network model inside Copernicus program built and available for everyone? So our answer to this is that actually it is possible to have very comparable results, especially on GPU. It could be even faster than FMask. But and also we were not using very new GPU. It was like 1070 GTX, and we believe that it also can be speed up even further. And for CPU, it is around 10 minutes, while other machine learning based methods for one Sentinel-2 products, the performance has like around 17 minutes. So we think that running time actually allows to use it in the big scales for processing the whole country. So why not to use neural network model as a as a model everywhere. So to summarize, we trained two models for LNC and L2A with Northern European focus. We published a data set which is free for the community, and we compare it with different methods. We're looking further for comparing these more deep learning methods and for comparing on other data sets. We also plan to extend our scope to the snow season, to some ocean areas, to the mountains, and introduce more area outside of Europe. To summarize, you are very welcome to try our cloud mask processor and to use our data set and check out our article. Thank you.
Right, thank you, Margarita. Very interesting presentation and good points. Is there any question from the audience? I don't see any question. Maybe a quick question from me. You showed the UNet at some point, Margarita. I was just wondering what's the precise input, if you can comment on that. I mean, how many channels, what's precisely in the input?
In our article, of course, we describe it much more details. We did hyperparameter tunings. We tried different number of input channels. In this model, we have 64 channels. If you need to have lower computational resources, 32 input channels is working also. Model with 32 input channels is also working quite well. So the difference in accuracy is really like 1%. So yeah, here is 64 input channels. Depth is 5 levels of depth. We also tried this with 6 and 7, and improvements weren't like that considerable. So we should we stick to the most lightweight and fast network without losing much accuracy.
Thank you, Margarita. I think we are running out of time. So no questions from the audience. All right, so we jump ahead. So I'm glad to introduce our third speaker, which is Christopher Rampasad. Hi, Chris. Chris is the VP of Engineering at Earth Daily Analytics. He has extensive experience working in space and ground segment engineering for several Earth observation missions, including the WorldView and Rapid Eye satellite constellations. He is currently leading the engineering team for the upcoming Earth Daily constellation, which is designed to image the world every day with scientific quality. Chris will present today improving geolocation quality with AI. Chris, okay, you can share, we can see your slides. The floor is yours.
Great, thank you very much, Leo, for the introduction, and hello, everyone. So I'll be talking about how we use AI for improving our geolocation and geometric quality within our pipeline for processing raw satellite data. Just a quick background on what we do. We at Earth Daily Analytics, we offer data services, satellite processing, and ML, specifically for areas of Earth observation relating to agriculture. And so with that, we're also developing our upcoming satellite constellation, Earth Daily. There's a little graphic depiction, but essentially it's designed to image the whole world every day, minus some small slivers around the equator at 5-meter resolution. What's unique about this mission is that it's really targeting to have high quality, so scientific quality that can match the other science missions like Sentinel-2 and Landsat. And so what that means is we're doing very rigorous ground pre-launch calibration for things like RSRs or relative spectral responses, but also really investing heavily on our ground segment technology to ensure radiometry and geolocation accuracy. And so this brings us to the backbone of our constellation. It's something we call the Earth Pipeline. And this is a commercially offered service which we offer to data providers of satellites. And what we do is we take the raw pixels, and it's in fact space packets that get downlinked to an antenna. We take those raw space packets, which are encrypted and they're binary, typically have artifacts prior to processing, and we push those through our pipeline and to generate analysis-ready data products. And as part of this process, we do satellite commissioning, things like the figuring out the point spread function, optical distortion, star tracker alignment, focal plane layout, that sort of thing. And just to give you an idea, when we talk about raw satellite data, most people don't typically see the raw satellite data. It's usually data providers provide the process products. So here's just a behind the scenes look at what raw satellite data looks like. So this isn't quite raw, it's almost raw, but this is a nice example of high quality push broom data. On the left is the raw data, and you'll see that there's stripes and the colors aren't balanced, and the pixels aren't even aligned to the ground yet. But once you put it through a pipeline, you can get very high quality location and reflected signals from each of those pixels. And so that's what our pipeline is designed to do, to transform the left to the right. And to do that, we apply a few technologies. The first is leveraging rigorous physical modeling. And so what that means is we do the modeling of the orbits, the attitude, the stability, optical distortion, and so forth. But what's really important is also to combine this with some computer vision and deep learning. And this is really important today, especially with new space, giving us the ability to put up satellites more quickly. So now we have smaller satellites, typically with lower cost star trackers and gyros. So they don't have the Sentinel-2 style hardware. And so what that's doing is it allows us to put satellites up more quickly, but we're actually moving the complexity to the ground because we need more sophisticated ground processing to achieve high quality. And this is where AI and deep learning can really help us. So here's 3 areas where we use some AI, computer vision, and deep learning within our pipeline. The first is in image correlation. This is to achieve both good geolocation and spectral band alignment between all the different bands. We also we had 2 great presentations on cloud detection. So we also use deep learning to help us with the cloud maskings for our pipeline service. And then the third area is in QA. Because we're offering a service level agreement with our service, we have to ensure that every product that goes out of our system matches the QA needs. And so that's really important for us to do that automatically. So I'm going to focus on the 2 green boxes for today. So one of the things that's critical for achieving high geometric quality is correlations. And so being able to match your satellite image to a base map, and you need a gold standard. So typically we use Sentinel-2 as our gold standard. And what we found at Earth Daily is that area-based image registration algorithms work far better for EO data than other key point-based descriptors like SIFT, SURF, and BRISC, which are fantastic tools. But for the MTF or the nature of EO data and the repeating scenes we see in agriculture, we find area-based are just more efficient for this. But area-based aren't in themselves, they can't handle all the different scenarios. They're generally not that well adept at handling scene differences. So if you're changing scenery from your Sentinel-2 base map to the imagery that you're processed, they have a hard time. And likewise, when you deal with different spectral bands, like the near infrared band and the red band, they look very different. And that's what you see on the bottom. Just some spectral differences make it hard to do image correlation. And so we wanted to use deep learning to help see if we could solve this problem, to help align near with red and near versus base maps. And so that's where we aim to develop something called ML Core, which we use internally for our pipeline. And that basically locks onto geometric features. And we want it to be essentially radiometry agnostic. And so what we did was we took some 18 million satellite image chips, and we used those to help train our deep learning CNN that we developed. And what we did was we evaluated those some independent scenes from Deimos 1 using 27 data sets where we took 5,000 random chips throughout those scenes. And what we found was when we compared our correlator, the new correlator, for red versus near, it did significantly better with this deep learning approach. So in this case, we have about 5,000 chips, and for ML Core, we get about 4,300 correct matches. The next best one we found is mutual information, which does a great job, and our custom, which is an internal one that we were developing in the past. But MI and our custom get you to around 3,700. So we're seeing quite a large improvement when you deal with some of these challenging spectral content like red versus near. The differences aren't so vast when we start going to more easier to correlate scenes like green versus red. Like we saw for near, it worked really well. So internally, we use that for helping to correlate chips for doing ground control points and tie point marking. But then the other part is once we process that product, how do we ensure that the quality is good? And as I mentioned earlier, small sats and CubeSats typically don't have multi-million-dollar star trackers. And so it's really important for us to ensure that what we've processed is achieving that big sat type quality to get 5 meters or sub-pixel quality. And so for us, we have SLAs, and that's why we've developed this automated QA tool. So our challenge is really to do this at scale and for edge cases. And so here's one example that is notoriously difficult both to process and also to QA because of the haze and the clouds. And so our initial product had an error of about 25 kilometers. This was a system without star trackers. And we were able to get the quality to less than about 10 meters and check that quality through our automated QA approach. And the high level way of how we do this is we have a routine to automatically find the places where we can actually mark ground control, because you can't mark ground control on water or clouds. That will give you false results in blenders. So we determine where to mark the points. And then the second part is once you find the points to mark, then ensuring you have a good correlator. And that's where ML Core comes in, allows us to do high quality correlations to validate the quality. And so in this case, we were able to assess it accurately. And in fact, this is one of the challenges, and I heard this come up in deep learning, in cloud detection as well. The training is really difficult. And for us, we had to do a really time-consuming process of doing this for thousands of images to ensure that we can trust the quality. So getting through this process and training is really key to achieving the good results. Here's just one other example. We had a very cloudy scene, and we're able to assess the quality of this after processing. And again, we can get it to about 10 meters or less than 10 meters after an initial error of about 30 kilometers. And again, the technique here is really about correlating to a gold standard. And so for us, we make great use of ESA because they have fantastic quality. It's a really pristine satellite. And we use that to correlate our other satellites to it. And likewise, we use our ML Core to validate our band-to-band registration. In this case, we're less than 0.2 pixels RMSE. And we find this is also really useful for hyperspectral bands. It allows us to handle those challenges. So at the end of all this, the whole point of doing this QA, the processing, is really about feeding this data into automated algorithms so we can extract value from that data. That's really the end goal. So here's an example of what happens when you run all these different satellites through a pipeline, and you can normalize the geometry. And here we have Deimos 1, Seaburst-4, Sentinel-2, Theia, and Deimos-2. We didn't raw data process the Seaburst-4 and Sentinel-2. We just did a refinement on those. The others are raw processing, but the geolocation of all those products are all really well designed, or really well aligned, I should say. And once you get that really well aligned, that in effect allows you to minimize the false positives that you get. And so then when you're looking for specific change, it becomes really easy. And you can find what you're looking for without having to worry about, is it a cloud or not a cloud? Yeah, that's a quick summary of how we address data quality and leverage AI for our solutions. Thank you all for listening.
Thank you, Chris, for your very interesting presentation. I think there's no question from the audience.
Yeah, I have a question, if I may. This is Valentina from ESA. I was wondering if you have any project running with ESA.
We don't. It's a great question. We do a lot of projects with the Canadian Space Agency, but we'd love to work with ESA. I was really intrigued by all the deep learning projects too that are happening. We'd love to make use of some of the work by Peter and Maharita. But great question, Valentina. We'd love to engage with ESA on some projects.
And have you ever tried to apply this method also to Sentinel-2 images? Because I understand Sentinel-2 is kind of your reference. So have you tried to use Sentinel-2 data in your method?
Yeah, so we use Sentinel, so we don't have access to the raw Sentinel-2 data. So when we use Sentinel-2, we do refinements on it. We do post-processing. For the other satellites, we go straight from the raw bits. But we correlate our images, our other satellite imagery to Sentinel-2. So we use it in that context. But we don't, we haven't actually run a QA against Sentinel-2 because QA is our gold standard. But yeah, we'd be interested to process raw Sentinel-2 as well. That could be an interesting thing for us.
Mm-hmm. And have you published any paper on this method, something that we can read?
So the ML core, because we're doing this as part of our service right now, we're not ready to publish it because it's for our internal service that we're offering for commercial reasons. We'd like to share some of the results, but right now we have a few proprietary things we're doing internally, unfortunately. So at this time, we're not quite ready to share, but hopefully in the future we'll be allowed to share more details of how the correlator works.
Yeah, it would be great if we can read more on how this works. And then I have just a comment. Next year we are going to make the GRI, so the global reference image that we use for Sentinel-2 data available to all the users. So it will be given for free and available to everyone, also as a database of ground control points. So I was just wondering if maybe it could be something that could be implemented in your method as an additional way to, let's say, adjust the geolocation, assuming Sentinel-2 as your reference.
Oh, that'd be fantastic. Yeah, having a base map for all satellites, I think is great, and using GRI, we would definitely adopt that. The other thing, which I'm not sure if ESA is at liberty of sharing, but a really high quality DEM that could also ensure that all other satellites are well normalized to Sentinel-2. But yeah, very much, we're very interested in that, Valentina. So we'd love to get on board and use those GCPs as well.
Okay, cool. Thank you.
Could I just make a comment about the very high quality DEM? I mean, the Copernicus DEM is published and is freely available. I believe that the resolution of that is 1 arcsecond or 30 meters, and it is global. So, and it is derived from the TandemX dataset. So, and recently there was a publication actually about the DEM terminology and definitions from the DMIX project, which is part of the CEOS Working Group CalVal Terrain Mapping Subgroup, which my colleague Peter Strobel from the JRC ISPRA chairs. So that actually describes that and a variety of other products. So that is available from ESA.
Great. Thanks, Peter.
And I'll send you a link separately. Well, I'll send it to everyone. And for some reason or other, Leo, we can't seem to chat with any of the people who are attendees. I just wanted to point that out because there was a comment made by my colleague, Dr. Francis, and I couldn't respond to it because there was no way I could respond by chat. But anyway, it may be something about the setup.
Guess so. Yeah, let me just go ahead with the next and the last speaker, and then I can check maybe the settings. Sorry about that. But in the meantime, yeah, let's go ahead because we're running out of time. Sorry about that. Thank you, Chris. Again, I'm glad to introduce now our fourth speaker, which is Kevin Hosser. Hi, Kevin. Kevin is a project manager and systems engineer for Telespazio UK. Part of the Earth Observation and Climate Group is over 15 years experience working on Earth observation quality control activities for ESA and other organizations. He is currently overseeing an internal initiative to investigate how machine learning techniques might be incorporated into traditional operation quality control activities for Earth observation data. She'll be talking about today. So Kevin will present today his QC insights from developing an AI-enabled quality control service for Earth observation data. We can see your slide, and the floor is yours, Kevin. Thank you.
Thank you, Leo. Good afternoon or good evening, everybody. I'm Kevin Halsall from Telespazio UK. As Leo said, I'm going to talk a bit about the EaseQC initiative that we're running in Telespazio at the moment and share with you a few of the insights that we've kind of gained from trying to develop an AI-enabled quality control service for EO data. So I'm going to talk a bit about EaseQC and summarize some of the results that we've had, and then move on to some of the issues and insights that we've gained. So a quick introduction to EaseQC, those who haven't heard of it before. Basically, this initiative was designed to try and address the rapidly rising volume of EO data and how you might deal with that for a quality control service. At Telespazio, we're responsible for the Ideas QA for EO service, which is one of the main EO QC functions at Esrin. And we were trying to work out exactly how you might keep up, as I say, with the rising volume of EO data for our QC activities using machine learning techniques. So as part of the initiative to date, we've had 3 linked projects, and they've looked at developing models to actually analyze and detect anomalies within EO data using machine learning algorithms, but also developing tools to support the development of those models and also the deployment of those models. So as a quick overview for the model types that we've looked at, there are 2 different types. The supervised, as we've termed it in this instance, looks at trying to detect a very specific anomaly type, one anomaly type in EO data. The example I've shown here is one we've termed the scan start anomaly in Landsat data. So we take lots of examples of this type of anomaly, try and synthesize more because of the limited amount of samples that we have. We create a training data set that we use to develop a CNN, and then we run that CNN against a test data set. So we successfully ran this model against a subset of Landsat data, and we were very pleased with the results that we got from the model. It was very accurate, and kind of demonstrated the legitimacy of the approach that we were taking. Then we moved on to a different type of model, a semi-supervised model. This is a more complicated model. It looks at, we basically teach it what's normal rather than teaching it what an anomaly looks like. And then it will identify products that are not normal according to its definition. So theoretically, it's able to detect multiple anomaly types. As I say, it's much more complex. And in fact, it's actually a chain of different machine learning models linked together. We're in the middle of that at the moment. It's proving, we knew it was going to be complex. It's proving slightly more complex than we thought. But we got some promising preliminary results. But effectively, we need more data to improve the model further. And that's something I'll touch on in a bit later. So as well as those models, we've developed a number of tools. The first tool I've brought up here, the QCult tool, I'm going to talk about in more detail later on. But it's effectively a tool that we designed for the QC engineer and the machine learning developer to use together. The other tool that we've developed, or tool set, is a platform that allows us to deploy models to where the data is, regardless of what platform data is being hosted on. And that integrates a number of services where you can deploy the model, run it against that data, and it displays the results in another instance of the QCOL tool. So that's a very quick overview of what we've been doing. But what I wanted to focus on for the majority of this talk is actually the issues and insights that we've got from trying to develop this service. So first of all, just to talk about service design, the guiding principle that we had with EaseQC is that we wanted to integrate the AI teams and the QC teams. AI development is often seen as something that you bolt on to something that already exists. But with the advantage of effectively starting from a blank sheet of paper, we could introduce the requirements and the needs of the AI teams into the service from the start. And that integration results in both processes being developed and also tools. And it's these tools, or this particular tool I've referenced before, QCOLT, we specifically designed that to bring the two teams together. So we have a tightly integrated process that relates to this tool. So if the QC engineers, they're able to use the tool to browse through image data, they can look at associated metadata. It also pulls in results from other separate QC tools. So effectively, it's a one-stop shop for QC analysis for the team. Then they can label or tag the data when they observe a particular anomaly within that system, within that product. The machine learning developers can then use that labeled data to define their training data sets and their test data sets. They develop the models, run the models against the test data, and then the results are imported into the tool as well. So then both the developers and the QC engineers can take a look at the output from the machine learning tools and look to see how those models need to be tweaked or the algorithms changed in order to improve the results that we're getting. And this is an iterative process to get the models to the required standard. We could do this because we were starting from a blank piece of paper, as I said, but this is not necessarily an approach that you can reverse engineer into an existing service. So kind of a recommendation is that, you know, if for QC services being developed in the future, significant consideration needs to be given to the needs of the AI teams and the machine learning developers, and build those into the requirements of the system as it's being defined. The second issue I wanted to talk about was that of data volume. So not just in this instance, in any instance where you're using machine learning, obviously data volume is really important. And the quality of the models depends both on the volume and the quality of the data that you're using. And that in part drove our decision to use Landsat data. There was a big archive that we could use to train our models. But in fact, actually, it's not the absolute volume of the satellite data that drives how effectively you can design the models. It's actually the volume of the anomalous products, because those are the products that make up your training data and your test data. So going forward with EaseQC, we need to expand into other sensors beyond Landsat, in part because we want this to be a multi-sensor service, but also because, as I mentioned, we want to improve the models that we have, and the semi-supervised model in particular, which we need more data for. This Sentinel-2 we see as the next logical step. Is very similar to Landsat data. We believe we can use that data to improve that model, and then use that model for both Landsat and Sentinel-2 and potentially other similar data sets. The Sentinel-2 is a good example of the issues that we need to overcome. Because Sentinel-2 is not, the QC service is not within ideas. It's not in-house with us. It's an external service. And that will be the case for many sensors. So the first issue is actually obtaining anomalous data. It kind of goes without saying, anomalous data is not actually easy to get hold of if it's already been detected within that sensor's QC service, because it's not generally made available to the public. But for our particular purpose, it's a useful resource. So we'd suggest that it would be useful to actually enable access to this data. Obviously, needs a level of segregation from the good, but opening it up would certainly allow people developing models to detect QC anomalies within data to actually get the examples of for the training data that they need. The second point is related to identifying which data products you need in your training data set. Different sensors, different services have their own methods of storing anomaly records. And there's an overhead for the machine learning development team to actually understand the reports that are produced and work out what data they actually need to put into their training data. The reports can differ in terms of where they're located, what their format is, whether they're even accessible, the level of detail, are they machine readable as well, which is important. So the final recommendation in this presentation is that if it was able to provide a consistent source of QC information across all emissions, that would be of a significant benefit. Now, of course, it's not practical to enforce the use of a specific tool or set of tools on pre-existing services. But perhaps a way to get around this is suggestion that you could add an additional layer of reporting to all QC services that's standardized. It does not need to be necessarily complicated, but potentially some kind of centralized database or machine readable reports, but that's designed specifically for machine learning developers so that they're able to easily identify anomalous products to allow them to develop the training data sets they need to develop their models. And that's it, Leo. So if anybody has any questions.
Thank you, Kevin. Very nice presentation. Is there any question from the audience? I see no questions from the audience. All right, thank you, Kevin. All great points, especially all the bullets at the end are very important for us. We actually thinking about setting up a challenge or a call for ideas on these topics, and that will be out later. So all those ideas are very interesting, and yeah, stay tuned on that. No questions. Got an email, maybe. Clement, do you have any question? I got an email from you, but maybe not.
Not to the last presentation, more an open question for it to be all the presentation.
All right. Okay. So we go to the next step, the final step. Thank you again for all the speakers for your great presentations and for sharing valuable views. So now officially we leave the floor open to the discussion. So anyone also from the attendees, please jump in if you want to share your views and you have ideas and suggestions, especially on what ESA might or should do, provide to help communities work towards AI-powered data quality. I have some questions, maybe to stimulate conversation.
I have a question. We saw very good, let's say, use of AI and machine learning to improve the quality of the data that it is for cloud, let's say, masking or band registration. So that was quite impressive. Have you considered, or do you think there is also a future for, let's say, quality control? So, for example, to detect the artifacts like stripping, banding in the images. Have you used it, and do you think there would be a use?
happy to start answering this question, but I feel free to jump in, anyone else. I think definitely the answer for us at Earth Daily Analytics is yes. For finding striping, whether it's deep learning or a computer vision approach, it should definitely be an automated way. I think having operators in the loop is very time consuming and very difficult. I think deep learning is a good approach. Right now, we use more computer vision for that kind of artifacts, but I think applying a deep learning approach would be really a good, even a secondary way, because having one mechanism is good, but you don't catch every scenario. So augmenting it with a deep learning, a more modern approach, I think would be a great idea, and something we'd definitely be interested in exploring further too. Can I turn the question around? Does ESA use any deep learning approaches for validating their sensor, their product quality for striping or artifacts?
Not yet. Not yet. There's a systematic quality control applied, but it's very, very, very simple. And as you were saying before, there's a manual, let's say, control, but only on a few very small amount of data.
Mm-hmm.
So maybe one way to explore would be to use a systematic quality control based on machine learning.
Mm-hmm.
That could be a direction.
We have some experience with applying it to a contained data set, which is 30,000 images of the surface of Mars, taken by the Viking orbiter imager. And we found that very, very helpful. I mean, we had about 12,000 actually hand labeled by a very enthusiastic master's student. But the point is that we got F1 scores in the upper 90s %. So it did seem to be a very effective way of detecting all those bad frames that we had. Now, that's of course nothing like as complex as the data that we have from Centaur 2 or any of the other sensors around. So I think it would still take a pretty considerable amount of processing, and also using a supervised method for doing that with such an enormous data set, I think would be rather problematic, which is the reason why I promoted the idea that we should be looking at self-learning systems, which are, I believe, a bit above 50% in terms of accuracy these days. But Kevin showed some examples of things that could potentially be used, and it does seem like a pretty obvious thing to look at in terms of using AI for kicking out those scenes that contain, and also isolating the parts of the scene that are affected by anomalies, not just the whole scene.
Yeah, it's a good point. We would have a training data set because we have service for checking the data. We could compile complaints, let's say, from users also for additional data. So we could have such a data set, but indeed would be a massive data set and a big effort. Okay, thank you.
Right. So connected to that, one of the points I wrote down in the slides was something Maravita was talking about, and it's point number 3 here. So how may we speed up AI for operational purposes? It's just a matter of using the right, let's say, computational resources, or can we do it? I don't know, maybe architectures wise or any other.
Well, if I just make a short comment on that, because I'll have to leave in a few minutes, but and that is the DIAS services and the TEPs at this point in time don't really offer significant GPU resources. It was something I was a bit gobsmacked by earlier this year when we were thinking of using those, and that's certainly something that needs to be improved. I mean, it is the case that GPUs exist for AWS and GCP, but they're very, very expensive services. And if we want to have something within Europe, that we can apply on a large scale, we need to start investing both ESA and the EU into these kind of services, because almost all of the machine learning is optimized to run with a GPU, and hence it's crazy to try and run this on the CPU where it's running 10 to 15 times slower.
Absolutely, absolutely. So your focus is more on the computational resources, right?
Yeah, because that would speed it up.
Yeah, sure. Maybe we can use this for clusters.
Sorry. Yeah, I wanted to comment too on this point. I fully agree with Professor Müller, but there is also a ways to make a model more lightweight. We can use also transfer learning and make transfer a big model knowledge into the smaller model, and then we'll use like much smaller computational resources as well. But yes, having GPU available is looks really essential right now.
Yeah, I mean, I agree. It's a combination of the two things. Obviously, there's lazy code writing, which, you know, essentially has whatever repeated steps which are not necessary to be done. They could be done by a function, for example. But from the point of view of ultimately for operational purposes, you need both the lightweight and the GPU.
I had a point. I had a question for you, Prof. Müller, on the super resolution. So how do you feel like, how good are those models radiometry-wise, sort of resolution-wise at this moment?
Yeah, when we started this work in 2015, we destroyed the radiometry. We were looking at multiple views, and in that process we got rid of the radiometry. The most recent models do not. The most recent models, which applied to Sentinel-2, actually preserve the radiometry, and in the publication that I mentioned in my talk, we actually describe and discuss that particular aspect, because we found that end users were rather aghast at the fact that they could only use it as a intensity for doing data fusion in HSI, for example, rather than be able to apply it to all the spectral bands and hence be able to obtain information on agriculture at the levels that they're interested in, which is in sub 5 meters and not in 10 to 20 meters.
Right. So thank you. We have another interesting point, which is related to physics-aware AI architectures. And a point was, how may we use those architectures that are physics-aware, or introduce this physics awareness to improve data quality related tasks? If you want to comment on that. Is it just a matter of changing the inputs, or?
Can make a comment, but I by no means have a good answer to this. One of the things that we found is ensuring you're feeding in the right data, and some of that data relates to the physics. So for cloud detection, you know, passing in sun angles into your CNN and passing in some of the math you can throw in into the problem helps, but that's giving it extra information, just picking the right parameters. And if you pick the physical parameters to help solve your problem, that does typically help you achieve a better result.
Yeah, I think presenting a wide enough range of scenes is one of the keys to that. So you cover the entire parameter range as far as you can with the training examples. But another approach, which is being implemented by DeepMind, I've seen a couple of presentations in the last few months at the Turing Institute in London, is where they are actually employing explicit representation of physics in the machine learning and achieving some pretty spectacular results, not in imaging, they're not there yet, but they are solving some problems in astrophysics by modeling the physics with the machine learning. So I think that that is something which may be on the time scale, 10 plus years, but it does definitely look as if it might have, as people in the US call it, it might have legs.
Mm-hmm. Kind of related, maybe, Prof. Mueller, you can comment on that. Do you all think, right, like when using super resolution, did you try to harmonize somehow the data, the training data before training? And do you think that this would help, like giving a physics awareness of something related to that to achieve better results in the radiometry perspective?
We prefer to use the actual data itself or high resolution data for the training, because the problem with pre-specification or simulated scenes, for example, I referred to earlier, is that they never ever encompass the range of noise that you have in a realistic image. And therefore, if you rely upon those kind of model scenes, which are created from physics, you are going to not be able to deal with the variety that you actually get in a real satellite image.
There were actually one book coming recently about geometric deep learning. I haven't read it yet, but the main claim is if you can introduce these geometric priors into the model and learn the symmetries, then like your performance will be better if you just learn it from the data. So I think this is definitely something that deep learning is going to develop, and maybe it will help also with this physical aware question as well.
Sounds good.
Thank you. I guess we're running out of time. Maybe the last open point could be, maybe you can comment out that, and how could ESA support these communities working together, working better together towards this AI-powered data quality?
Set up challenges and provide appropriate resources.
That's a good tip.
By resources, you are talking about processing resources, but also test dataset, I imagine, training dataset, validation dataset, and
That's correct.
This conference is also a good thing for visibility and meeting each other.
there are so many topics that could be addressed there. How do you think we should pick or decide which topic the community would like to address, in addition of discussing in, let's say, workshops like this one?
Well, the level 1 data products, the things that applied at level 1 to create level 2 products: atmospheric correction, BRDF correction, cloud detection, all of those things which are fundamental and core to all the derived downstream products. Those are the ones that I think ESA should be focusing on, because of the fact that the community will obviously work on the level 2 to level 3 products, because that's the value that they're adding. But something that ESA could definitely add would be that for the level 1, which has already been started with CMIX and so on and so forth. But the fact is that it needs to be wider. It needs to be set, and also the computer science community that developed many of these techniques in the first place, they can come up with some very novel solutions if you can invite them in. So I think also getting non-traditional remote sensing people involved would be helpful.
So do you mean like advertising intercomparison exercises as a CMIX and ASICs also in these AI communities?
Yes, and also we've done this before in EU projects, and we even offered a prize, which in this particular case was a free flight to JPL to actually visit the Mars. But I mean, you could offer a prize which would be appropriate for whatever it is, a weekend in Rome. No, but basically you could offer a prize for that, which would be, a public recognition of that work.
Okay,
Right. So there was a comment from the attendees. Helen commented on question 3. If the model is trained, you can share the weights of the model. One can use this to do what is called an inference. Yes, of course, you do that. And I mean, the point was more on what Margarita showed us, that when you do inferences on a lot of imagettes or patches, time can increase a lot. And Prof. Mueller, in fact, commented on architectures. I mean, sorry, computational resources. All right, so if you don't have any other point, Clement, Valentina, or any other panelist or speaker, any attendee, I was extremely happy to host this side event within the fourth edition of the Phiweek. Again, thank you, all the speakers and all the attendees and my co-hosts, for all the great presentations and the contributions. Yeah, I mean, we over. Thank you, and we can maybe meet later during this year, hopefully in person at some point. And again, big thank you, massive thank you, and this concludes the side event, and you may have a wonderful one.
Thank you. Have a nice evening.
Well,
Bye-bye.
Thank you, everybody.
Thank you for the invitation. Bye.
Bye.
Thank you.